Hi, everybody. This is Mr. Karlovsky, and we're going to move on today to the second part of 9.4. And I want to tell you a little story. A little story about a little bug. I don't know his name, but a little bug here. And he is on the floor, and he sees 40 feet away some delicious food. Oh, he needs that food. And this bug is so excited that he jumps 20 feet. Boom, jumps 20 feet towards that food. He's so excited. And that's where the bug is now. And this bug is so excited that then he's kind of overexerted himself that now his second jump, he can only jump half as far as he did before. So his next jump, although he's excited, he can only go 10 feet because he was so exhausted from that previous jump. All right, and so now he is clearly at 30. And that's our bug. So the bug who jumps half as far every jump. And that's the story. Okay. So this bug is going to keep jumping because he wants that food. All right, so it's obviously kind of a silly story, but let's talk about the math behind it. Now, as a sequence, if we think about his jumps as a sequence, well, then his, let me write that down. So as a sequence, hopefully you can see this is clearly geometric because of the concept of half. Half is a multiplier of 0.5. So we know that the sequence is a first jump of 20, then a half would be 10, then half would be 5, and so on. So his jumps are going to be getting smaller and smaller by half. And then, connecting to last class, if we think of it as a series, where it's the sum of the jumps, right? It's not just the individual jumps, but progressing towards where he wants to go. Well, then, what would be? Well, his first jump, he's gone 20. But then now the sum of the next jump, well, now he would be at 30. And then now the third jump would be, he would make it all the way to 35, right? So I'll even draw that in there. If he made one more jump, he's now at 35. Boy, he's really close to that food. Okay, well, now the concept is, well, let's jump forward, no pun intended. What if we get to jump, let's say jump 7. Okay, so he's now jumped 7 times. Where is he? Well, first off, let me find out how big that 7th jump is. That's a sequence. So his 7th jump would be the first term of 20 times the R value of 0.5 to the 7 minus 1, right? So a little good review of geometric sequences. And so how big is that 7th jump is 0.3125. So, boy, he must be really tired. His 7th jump is very, very short, less than half of a foot. Okay. All right, well then, now what's the sum of those 7 jumps? So this is from last class. The sum of those 7 jumps would be the first term 20, 1 minus r to the 7th, all over 1 minus r. So this is a nice little review of geometric sequences for the above calculation, and now geometric series that the sum of those 7 jumps is 39.6875. Oh, he's so close to the 40 feet where all the food is. All right, well, you might be seeing where this is going, so let's just go one more. What if we go to jump 10? I'm going to squeeze this in here. So now his 10th jump, all right, so he's been jumping. His 10th jump is 20.5 to the 10 minus 1. I bet that's going to be a very, very small jump. And this jump is so small, I'm going to have to round the decimal 0.039. A really, really small jump. Well, that's okay. He's still jumping. What's the sum of those 10 jumps? Well, 20. 1 minus 0.5 to the 10th, all over 1 minus 0.5. And now he's jumped 10 straight times. How far has he gotten? 39.961. So this poor bug, he's been jumping for 10 straight jumps, and he's not quite at the food. He needs to get exactly to 40 to reach the food. Okay, so what we're developing into is this concept of an infinite geometric series. That's really all we're trying to do with this example, is what happens if the bug jumps forever. Not 100 times, not 1,000 times, literally forever. And it's a really quick connection in that we already have a formula for a finite geometric series. Let me write that down one more time. A sub 1, 1 minus r to the n, all over 1 minus r. Okay, so we have this as for any number n terms. We could do 1,000 jumps, 1,000,000,000 jumps, right? That's a number. That's what n is. Well, an infinite, basically, and it's a good connection to the idea, is what happens as n approaches infinity, right? We can't plug in infinity. We can only approach infinity. And let me just get to it, and then we'll talk about it. We have that the infinite sum, and we actually write s sub infinity. If the bug jumps forever, then where does he approach? He's going to approach just a sub 1 over 1 minus r. And that's the formula, okay? So I'm going to throw the formula at you first. Now let's discuss what happened. Well, this worked because the bug's jumps kept getting smaller and smaller and smaller. Now, why was the jumps getting smaller? Because his r value was 1/2. So what happens is that since r is 1/2, this piece of the series, r to the n, is going to approach 0. Think about why that is. If r is 1/2, or any number smaller than 1, powers of that smaller number are going to get smaller and smaller and smaller and smaller all the way towards 0. And what happens is that if this part basically becomes 0, well then 1 minus 0 is 1, and then we have our formula on the right side. So therefore, what's important is that this only works if the jumps get smaller, meaning if r is less than 1. And we're going to go one step further that, you know what, the jumps can get smaller but still alternate because r could be negative. So I'm going to say the absolute value of r has to be less than 1. The jumps are still getting smaller, but maybe they're alternating. I think of it as the bug who jumped forward 10, but then backwards 5, and then forward 2.5, and backwards. And if you think about it, if he keeps going back and forth, he will still reach a number somewhere in that gap. Okay, all right, a lot of abstract stuff. So first off, let's see what happens with that bug. With our bug in the first example, we would say that the sum, if he jumps forever, is his first jump, which was 20, sorry, it was 20, all over 1 minus his r value of 0.5. And guess what? That is exactly 40. So the answer is he will reach the food if he jumps forever. Not, but if he ever stops, even after 1,000,000,000 jumps, he won't be there. He'll be at 39.999999, etc. Okay, so it's a really kind of a weird concept and one that would be hard to talk about if we were in class. But an infinite sum, it only is that exact value of 40 if it jumps forever for infinity. Okay, so again, that's what it is. Let's just do a quick second example, and I'll keep talking about a bug jumping, but let's say the first jump of the bug is, I don't know, 18, and let's say his R value is negative 1/3. Okay, so that I threw in the negative just to make it be where he's jumping forward, then backward, then forward, then backward. So if we just visualize it, so here he is, he jumps forward 18, and then he's going to come back, but it's going to be a third, right? So if he comes back a third, well, that would be 6, so he'd be back here at 12, and forward, backward, well, let's see where he ends up. Well, according to our formula, the infinite sum is the first term 18 divided by 1 minus r, and r is negative 1/3. So even though the absolute value of r has to be less than 1, you still plug in the actual r value of negative 1/3. And so if we go to your calculator, that's 18 divided by 4/3, and not the prettiest number, Actually, it's not that bad. He ends up at 13.5. So he'll be jumping right around 13.5, but if he jumps forever and ever and ever, he would end up at 13.5 exactly. Okay, so that's an infinite geometric series. And again, the reason it's so nice is that, like I said, it's only first off, only for geometric, and only if the R value makes the term smaller. So there is no infinite arithmetic series, that because those terms, the numbers get bigger and bigger and bigger, so the infinite sum blows up towards infinity or negative infinity. So there's a really kind of just a one example of infinite geometric series. And where I'm going to finish with just kind of a neat example, not talking about a bug this time, but I bet you all agree that point 0.3 repeating, which of course is 0.33333, dot, 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 that equals 1/3. I bet you all agree that point 0.6 repeating, which is 0.666, dot, 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 is 2/3. And therefore we go, well, then what should point 0.9 repeating be? Well, if 0.999 in the pattern 1/3, 2/3 means this should be 3/3, which means exactly 1. And we're going to talk about why it is true that 0.9 repeating is exactly 1. And it's a really, really quick example using our geometric series. Because 0.9 repeating is 0.9999. I'll just do a couple there. Well, 0.99999 is 0.9 plus 0.09, right? That's where the second 9 would come from. Where would the third 9 come from? 0.009. And then the fourth one, 0.0009. And dot, dot, dot. And so this is an example of an infinite, because of the dot, 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 it goes on forever. And then why is this geometric? Well, look at this pattern from from 0.9 to 0.09 to 0.009. That's an R value of 0.1, 1/10. The number's getting smaller by a tenth. And so because it is infinite and it's geometric and the R value is less than 1, making the term smaller, we could do that the infinite sum, because we are adding these forever, is the first term, 0.9, divided by 1 minus the R value, 0.1, and that's exactly 0.9 over 0.9, and that's exactly 1. And that proves that 0.9 repeating is exactly 1. Kind of a weird thing to say. People want to think, no, it's just a little less than 1. Well, yeah, it's less than 1 if you ever stop the nines. If you ever stop the nines, then yeah, it's a little less than 1. But if the nines go on forever, it's exactly 1. Okay, so that was this part 1 for today, the infinite geometric series. And now we're going to move on to part 2.